All right, welcome all to my EDA model analysis presentation. This project is done for my machine learning supervised learning class from the University of Colorado Boulder. Um, Data set I decided to use was a data set from GoodReads. GoodReads is a website where people can share their opinions about different books. Um, his data set is quite large. It has a little over 52,000 books, and it's about the main purpose of this data set is so people can vote for what they consider the best book ever. So this is the best book ever data set. Um, Quick look here on the data set itself. You can see there are many different features for each book. So some of the features are price, the best book ever score, number of ratings, how many pages each book has, the description, the title, and so on. Obviously, I won't be using all of these features as I don't think that would be practical. So I decided to go with four different features that we're going to talk a little bit more soon. All right, so to get started here, let's talk about the problem definition. So I'm curious to understand why people chose a certain book as the best book ever. So I want to know if there are any features in this data set that can predict the best book ever votes or score. And if so, how much of a prediction will be? Is it relevant? Is it not relevant? So basically, that's what I was trying to get at. I decided to go with four features for comparison. We'll talk a little bit more about that soon. So let's start here. Let me run all the cells. As you can see here, we are importing the necessary libraries and we are starting our data set here. As it's a pretty big mess. There's a lot of unclean data, let's call it, and also data that we don't need. So we're going to go through data cleaning soon as well. Here's some information about the data set. So the data set has a little bit over 52 rows, 52,000 rows and 25 columns. Each column, as I said, is a feature, or at least I'm calling it features. Just information about the books as we discussed before. Um, Again, some of the features here, we have the ISBN number, which obviously is irrelevant for what we're looking for. This tends to be quite a random number or identification for the book, so that wouldn't influence how people vote or not vote for what's considered best book or not. And then some more meaningful or more relevant features, such as rating, for example. Rating that goes from 1 to 5, 1 being not too happy with the book, and 5 being this is an amazing book. And here is some information on missing values, so null values. We can see here some features have very little or no missing values, and some features have a very high number of missing values. So for example, series has 29,000 missing values, which I believe is just under half of the entire data set. But we are not considering those. So again, we're looking at rating, which has 0 null values. We're looking at, let's take a look here, awards, which has 0 null values, number of ratings, which has 0 null values, and then liked percent, which has some missed values. But as a reminder, this data set has 52,000 rows, so having 600 missing values is not a huge number, and we'll take care of this with our data cleaning. All right, so this is just a way to visualize here the missing values. So we can see in purple are the rows that do not have any missing values, and yellow are the rows that have missing values. So we can see here addition seems like an entire, almost in its entirety are missing values. I believe, let me take a look here. Yeah, edition 47,000 missing values. So the majority of books do not have that information. And then many of the columns, and especially the columns that we're looking for, have, for example, BBE votes have no missing values or very little missing values. All right, so let's take a look here at the data cleaning. We can go over some of the things I decided to do here to prepare the data before we apply our models to the data set. First thing I did here was for award counts. So let's take a look here at award counts. As you can see, award counts is not a number, it's the name of the awards. It doesn't even have how many awards a book was granted, which is what we're looking for. So what I did here is I just converted this to a number, so we know how many awards was earned by each book, and then I did the same. I converted to numeric values for everything else, even for things that you might assume is already numeric. For example, number of ratings. We might expect that's going to be a number, 10,000 ratings, 5 ratings, but it might still be seen or written down in the data set as a string or something else. So we're just making sure that these are all numeric, that these are all integers or floats. All right, so we did a little bit of feature engineering here. I had to apply a log transformation to these values because some of the graphs were very skewed to the left or right. Just as an example, if you think about number of ratings, for example, let's take a look here again at our table. The first book there has over 6 million ratings, right? And then if we go down the list, we're going to see some books have 6 ratings or 10,000 ratings. So the problem with that is that when we are trying to visualize that in a graph, you're going to have a huge rectangle for the ones that have a lot of votes, and then you can barely see the ones that have very few ratings. So to solve that, all we have to do is do a log transformation, and that solves that problem partially. Let's go down here. One thing I wanted to mention was that I forgot was the type of problem here. So this is going to be a regression problem. The target variable, the BB vote, is continuous and numeric, which is a key characteristic of regression problems. The models that I'm going to use is going to be linear regression and random forest regressor. They're specifically designed for regression tasks, so I think it's appropriate for this context. And the metrics I'm going to be evaluating is mean square error, or more specifically the root mean square error, and R-square scores. They're typical for regression problems and very useful. They, as you probably know, they measure the difference between the predicted and the actual continuous values. All right, so let's go back here to our data cleaning. So here I'm just stripping some columns to make sure there's no leading or trailing white spaces, so that won't be any problem in the future when I'm calling a variable or trying to manipulate my data set, my data frame. I'm dropping here all the rows with no values. We saw before that the only one with no values for what we're looking for is like %, but it doesn't hurt to drop everything else just in case this data set is updated in the future. This will take care of that if there are any no values. So as mentioned before, these are the features of interest: rating, log award counts, log number of ratings, liked %, and log BBE votes. Some values are set to infinite. So what we're doing here is replacing those values with a finite number and dropping them because they're gonna skew the data heavily. We don't want them to get in the way of us visualizing the data. All right, so we're gonna drop all other columns here, and then we're gonna use a scalar and also the IQR method. I use the IQR method to detect and handle any outliers in the rating feature. All right, so we can see here the clean data. So now the columns are just these five, and the clean data is right here, the first 5 rows. Just some information here on the standard scalar and what it is used for. So it transforms the data such that it has a mean of 0 and a standard deviation of 1, which is crucial for many machine learning models, particularly those with sensitive to feature scales like linear regression. That's why if you pay attention to the results above, award counts can be a fraction or even a negative number, right? So it's not like an author has a negative number of awards. Obviously, that's not possible. That just means that they are under the average of all the books, all the number of awards of all books. All right, so the data cleaning conclusion and discussion. So as a summary here, the data clean process involved standardizing formats, handling missing values, and ensuring data integrity through removing duplicates and outlier removal. The dataset is fairly clean with only a few missing values in some columns, which were addressed through imputation and removal. Some of the challenges here for data cleaning was balancing data completeness with the need to remove unreliable data. We don't want to remove too much. Luckily, most of the values I was working with were not missing any data, or most of the features I'm working with are not missing any data. And then we focused on retaining as much data as possible or ensuring quality for analysis and modeling. All right, so let's take a look at the EDA and visualization here. So this is what IQR is doing for us here, and also a log transformation. It is helping us visualize this better. Just imagine ratings, for example. If we think about the actual counts, some books have millions of ratings, so you would see a massive column right here, and it would be very hard to see other books here because of how skewed that would be to the left. So what this does for us is tell us that most books are on an average here rating, and then there's a very small number of books that have very high ratings and very low ratings. Same thing for the number of ratings, right? So the number of ratings is just how many ratings a book got, and the rating is a 1 to 5 grade, let's say. And also the same thing for award counts. Now, award counts, you can see here that you have some books, or actually the majority of books have 0 awards, and then in a decreasing manner, less and less books have more awards. All right, so a quick comparison here between BBE votes and other features. So the overall takeaway here is that the standout relationship is between the total ratings and BBE votes, right? So if we take a look here at the third graph, you're going to see how this forms a nice upward line towards number of ratings. So as the number of ratings increase, the BBE votes also increase. You see some similar results with light percent, but not to the same extension, or to the same extent, excuse me. And then you don't see the same results with log awards and also with rating. It's the distribution is more spread out, and you don't see a clear pattern here. All right, so if we go down here to the analysis and conclusion, so you're going to see, as I mentioned, so the rating in BBE votes or rating has a weak but positive effect. Then let's go here to number of ratings. So is the strongest predictor of log BBE votes among the feature analyzed. And then the liked percent comes in second. All right, so here's my correlation matrix. So you're going to see here my correlation matrix how the strongest score for the correlation matrix for BBE votes was with the number of ratings. Okay, so that showed a stronger correlation, and then also you have awards count coming in a close second. Rating and liked percent was still a positive number, but a very small, almost insignificant number. All right, moving on to correlation matrix analysis. So I think we already talked a little bit about this, but it shows the strongest positive correlation with BBE votes was number of ratings coming up at 0.56. So in other words, books with the more total ratings tend to receive more books, best book ever votes. All right, so now let's talk about our first model. So I chose linear regression. I chose linear regression because it provides a baseline. I can use this model to compare with other models. And then linear models are computationally less intensive compared to nonlinear models, making them suitable for large data sets. This is a large data set. And then linear models are easier to interpret and understand, making it easier to understand the relationship between the features and the target variable. So the problem set here is to predict the rank of a book based on its rating, total number of awards, liked percent, and number of ratings. So the rank of a book is just how many BBE votes, best book ever votes they have. To achieve this, I'll use the linear regression model as mentioned above. So to evaluate the model, I'll use the RMSE and R-squared metrics. So we can jump here to some of the results. So you see the root mean square error is 0.8 and R-squared 0.36. The coefficients you have 0.64 for log, number of ratings, 0.36 for rating, 0.12 for award counts, and minus 0.34 for liked percent. We can see here a little bit of a graph showing us these results. So obviously the best feature here, the most important feature is going to be number of ratings and followed by rating, the rating itself. So how many ratings a book have and then what rating it has, right? So the biggest rating, the more the prediction of BBE votes, and the more ratings, the best that would predict BBE votes, which makes sense, right? If a book has more ratings, it's more popular. If it's more popular, it's more likely to have people voting for it as BBE votes, as a best book ever. Second model I used was random forest regressor. So it does handle nonlinearity well, all right? So it can capture complex relationships between features and the target variable. I do think these are complex relationships. It's not extremely clear that one can successfully predict BBE votes, and it's also not clear that only one can predict. You'll see at the end that even using 4, there was still some prediction that were not accounted for. So it's also robust to overfitting. So generally more robust to overfitting than individual decision trees, especially with a large number of trees. And the feature importance, so it provides insights into feature importance, which can be useful for understanding the model. So feature importance, right? So how important is the 4 features that I am analyzing compared to BBE votes? All right, so we can take a look at the results here. We see here the root mean square error is 0.60, R square is 0.64, and then the importance, you have number of ratings 0.82, rating 0.09, which is a much smaller relevance there, and then like percent 0.05 and award counts 0.02. So here is a good graph to visualize what we just saw above. We can clearly see that although all features have a positive correlation with BBE votes, number of ratings is by far the most important feature. And if we go back here, we can see that it's the same case for our linear regression model. That's at least good news that both models return the same result or similar results. So let's take a look at the results here. So for the linear regression, so the R square was 0.64. The model explains about 64% of the variance in best book ever votes. So that suggests these four predictors capture a significant portion of what drives BBE votes, though there is still room for unmeasured factors. As you know, we could have predicted that because there's a lot of different variables here that we're not looking at. So it is not surprising that that's the case. And then if we go back here, so the root mean square error is 0.61 for a linear regression model on the log scale. So that would translate to moderate predictive error for BBE votes. So it's decent for a simple linear model, but it is not tight, right? So it's not the best result we could have seen. So for the coefficients, for the features, so we have number of ratings, by far the largest positive coefficient, as we saw before. Rating and like percent are both positive, but smaller in effect. And then, as we saw, award counts has a positive, a very modest relationship. So, 0.03 is nothing to write home about. All right, so the random forest regressor, we're going to see here. It achieved an R square of 0.64, as we saw on the test set, which means it explains about 64% of the variation in the log of BBE votes. And then the root mean square error was 0.61, and that indicates that while the model predictions are reasonably accurate in log space, there's still some explained variability, right? So we are seeing the same results here for both models. So for the coefficients, again, number of ratings is by far the most influential predictor for log, the log of the BBE votes. Rating, like percent, and log awards are also positive, but they have a very small prediction value. So just as a final conclusion here, no, I'm running a little over the time that I had, but just so we can finish, so both models seem to indicate that the number of ratings is the greatest predictor of best book ever votes, and that BBE votes predictions could benefit from adding more features to the models. All right, thank you. I will post this on GitHub, and I will post the link on the platform, and we'll go from there. Thank you.